Well, good morning, everybody. Welcome to another one of the seminars or webinars presented by Electromechanica. It is a series of webinars that we present. So my name is Jaap Grobler. I'm the host for today, and we are shared with Arthur Soka. He will then share his knowledge and his expertise today with us in the world of power factor correction and harmonics. So before we start, maybe just a couple of house rules. Please have your 2020 Electromechanical catalog handy, because Arthur will be referring to the catalog quite often. Then also, as you will notice that your screen has been frozen, your audio is muted, in order to be sure that we have the best possible communication media. You will see it. Maybe Arthur, go to the next slide, please. You will see that at the bottom of your screen, you will have a chat function where you can then communicate with as a general message to everybody. Or if you would like to verbally ask a question, you can raise your hand. We will then unmute you, and then you can ask the question. Mostly the Q&A session is used for questions and answers. So if you have a question and you don't want to do it verbally, please type the question, and then we will answer the question there. This webinar will be recorded, and then it will be available to you after the webinar. Also, we ask you to complete the poll at the end of the session. We still have a number of webinars in line, and we always strive to have it as best as possible, and your feedback will be well appreciated. So without further ado, I hand you over to Soka, and he will enlighten you in this world of power factor correction and harmonics. Thank you, Arthur.
Good morning. Thank you, Jaap. Thank you for the introduction. So myself, product manager on the power factor, power quality side. I also look after our EM technical team, so covering quite a couple of areas for our customers. So the purpose of today's session would be to provide the highlight to what power factor is and harmonics, followed with products and solutions that address or help address these situations we find ourselves in. Okay. All right, so to start off, we are split over 2 sessions with a short break midway. In the first portion is obviously, as we said, introduction to power factor, understanding how the savings are achieved, calculated the estimated savings, and an introduction to harmonics. Okay, so I think something quite a couple of us missed during lockdown in certain countries is, what we did here was no access to beer. So we would use the beer analogy for power factor. So I think we all enjoy a beer at some stage, and we do realize that we have to pay for that whole glass of beer. So using the power factor relation, what is power factor? Simply, it's the name given to the ratio of actual power in kilowatt being drawn by or used by the circuit, and this is typically noted in watts or kilowatts, versus the apparent, the kVA power being totally used for the circuit. So that's the system capacity. So that is what you would be paying for. And then we've got the wasteful components, which in our case is the foam, which is the kVAR. So as with the beer, you pay for total system capacity or the total glass of beer. The wasteful foam, the kVAR, is what we want to reduce when we purchase or use our supply. And active power is the active useful work being done. So in our case, the actual liquid that quenches our thirst. All right. This ratio is relatively simple. It's a number of a point something factor up to a 1. So simply calculated, if you looked at your demand and your kilowatt, you would deduct kilowatt by kVA, and you would be left with a number. And that power factor number, that ratio, is what we commonly use within all our calculations. So what causes low power factor? So as we know, all modern industries would use energy. The two basic categories that are encountered typically in AC circuits. Highlighted in green, resistive loads. These loads draw current from a supply and are directly converted into something useful, so being heat or light, resulting in what we would call kilowatt. So resistive load being a heater, a lamp, a soldering iron, the direct result calculation would be kilowatt. So in equals out, useful power, or it is directly converted to something that is useful. So in our example, the generator, the utility, supplies light in kilowatt, and it is considered a resistive load. The more common one applied on motors, and this is the one that causes low power factor, is what we would call inductive loads. So all motors, transformers depend on magnetism as their basis of their operation. In AC motors and transformers, magnetic force is only required in a period of that transaction. So the electric current needed for that is not fully utilized. So inductive loads require two kinds of current. As mentioned on the previous, working power, kilowatt, which performs the actual work in creating heat, light, motion, machine output, and so on. And then the reactive power to sustain this magnetic field. So if we view our little image here, we've got the generator, supply and return, and we've got this magnetic field, which is the force that we have to overcome. Working power and reactive power together, so the two forces or types of current combined, make up what we call apparent power. So apparent power is measured in kVA. Okay. The types of loads that would affect us are transformers, induction motors, heating, HID lighting, welding, arc and induction furnaces, as per example. Power factor can be unity, lagging, or leading. So in the perfect world, we would have, let's say, unity power factor. That is typically would only exist if your whole circuit was resistive. And that is the ideal situation we'd want to be in, where the voltage and the currents are in phase, and there's basically no wastage. When we move to a lagging power factor, and that is what we try and correct with power factor correction, when current lags behind the voltage, the power factor in that circuit is then considered to be lagging. This is a result of the inductive loads. Another form that we would have is leading power factor, where the current the current leads the voltage. The power factor would then be leading. Okay, what causes leading power factor is a capacitive load. Today's focus will be on lagging power factor. Okay, what should a customer improve or do to improve their power factor? Why? So what is the disadvantage of a low power factor? Is of course increased energy cost, which is directly billed to customers on a maximum demand kVA. So you would have customers, when they look at their utility bills, the larger suppliers would have a kilowatt hour unit charge, and they would have a kVA charge. Okay. Also, a low power factor, as it's not useful, it would overload the transformer and distribution lines, resulting in a greater voltage drops and power losses. Okay. Reduced handling capability of a plant's electrical system, the penalties from the utility, and voltage drops, which could cause motors to slow down, require more current to produce a fixed torque for loads. So the benefit of improving power factor is not just directly a finance benefit, it is an operational benefit for your site and relatively simple to implement. How can a customer improve their power factor? Look, the most economic way and fastest way is by using an automatic power factor system, such as what EM would assemble. What the system does, it would bring in the required capacitance, and this capacitance creates a phase angle change. So capacitors would produce capacitive reactive power, which is exactly vertically opposite of inductive reactive power. So if we look at our little power triangle we've got here, we've got our demand, our kVA, we've got our kilowatt, and we've got our reactive component in kVAR. How is power factor corrected? So we will stick to our beer analogy. As we said, kilowatt over kVA would give us our power factor number, all right? So let's call this the cos pi, and it's this angle we see here. By calculating this power factor and the required kVAR, to improve the power factor to a 0.98 or a 1, we would need to adapt or bring in what we call capacitors or capacitor banks, which are in parallel with the circuit. So the system would measure, see the requirement, and bring in those banks. So viewing our analogy here, this was my original system, and this was my reactive power. I then brought in capacitance with the capacitor, and I reduced my kVA to get closer to my kilowatt. So a smaller gap equates to a better power factor and a reduced electricity bill for the charges on kVA. Methods used during application of power factor correction systems. So where would we install these, or where would customers install these? In obviously large industrial plants with many motors. It would be seen at what is the objective, so to obtain a lower electricity bill. So what we'd call central compensation is more practical and economical than individual motor compensation, which we'll cover. What would happen here is, if you imagine that was your site and your total load, you would, on the main incomer, on the LV side, connect your power factor unit onto that bus bar, as an example. Then you would include a set of CTs, which would measure the total site load to be able to correct that reactive power shortfall. So this can be done on the main incomer, in this example, or further downstream. Why would I install it further downstream? It may be to do with cable issues. So overheating cables, obviously you would then try and correct it closer to the load that's creating that problem. The financial benefit is typically, in this scenario, immediate, because your metering or your utility is billing you on the LV side. So the better it is, your power factor at that point, the better the reduction would be on your kVA charges. Another method to be applied, that used to be applied a while ago, is what we'd call individual motor compensation. So at this point, the actual compensation or the capacitor is installed directly on the motor. All right. Effectively, the correction is then done at each motor, obviously. The capacitor rating should be matched as close as possible to the motor being corrected. Do not overcompensate. And another very important point would be, what is your disconnection method with that capacitor? We've seen sometimes historically the customer would literally connect that capacitor straight onto the motor. The problem you would have there is, depending on the function of that motor, imagine it's driving a fan or something, for example. When the motor is stopped or the voltage supply to the motor is stopped, the fan could continue to make that motor turn. In that case, that energy is then transferred into the capacitor if that capacitor is not disconnected from the circuit. What happens then? It will cause what we call over-excitation onto the motor. All right. So how do you prevent that? Make sure when the load drops out or the power drops out to the motor, ensure you step out the capacitor at that point in time. This method of individual is getting less and less. A lot of customers would be doing complete site compensation instead. It's more feasible, it's more practical to maintain one system than multiple little systems all over the site. The end benefit on kVA reduction on the billing is still obtained on the main. So what sort of questions would we have for our customers that are querying power factor systems? So we'll get a call, the guy might phone you and say, oh, I've got a 63 amp three-phase supply, do I need power factor? Probably not. It's really dependent on your charges that you get from your utility. So first question you would ask your customer is, do I get charged on a kVA demand on my utility bill? Ask them for the utility bill. You'll be able to see or identify if there's a kVA charge. Next question to ask is, do you have electrical recordings available for the site, the load profile? Preferably detailed recordings with at least 7 days worth of data, and harmonics contents, which we'll get to. Important question to ask, what is your network voltage? 400, 525, 690. Do you have a stick configuration of the capacitor banks? Typically, to be able to do that, you would need recordings. The big question is, do you have harmonics on your electrical network? Okay. Now, for 4 and 5, it's going to be very difficult without. Point 2 is do you have recordings with harmonic contents for the site? How do you size the power factor system for a customer? So as discussed, we would need a corrected load profile or the correct load profile of the customer using a power quality logger. Typically, we would request 7 days and 1 to 5 minute intervals, including the harmonic content, which we will get to later. Typical data as a minimum, we would need peak kVA, the maximum demand, the peak kilowatt, the power factor ratio at the peak. We can calculate that, but it's great to have that off the recorder. The continuous network voltage during all this recording. If you've got the charge from the customer on the kVA charge, that's great, because that will immediately give you your calculation of what is based on my reduction of my kVA, what is my savings from the utility. And then the big topic would be the total harmonic distortion levels and the total voltage distortion levels. With this data in hand, the calculation can be done to determine your capacitor size requirements for the system. So in our example we have here is the plant in this case. So convert the plant load to kilowatt. So this plant had a 400 kVA peak at 0.7. So we did the conversion here, 400 kVA times 0.7, and we got our kilowatt rating. So to correct this 400 kVA at 0.7 to 0.96, we would follow the table to 0.7, scroll across to 0.96, and we've got a ratio number of 0.729. We would take this 280 kilowatts, which we calculated as the useful power, and would multiply it by this ratio, and we get our kVAR. So you would then identify, I had 400 kVA, I applied 204 kVAR to the system at that peak. I reduced it to 292 kVA. The reduction was 108 kVA. What we have done is, as EM, to simplify for our customers, you can do this table if wanted, or you can make your life a lot easier and try our calculator on our website. The end output, the result of this calculator, is the exact kVAR that you would need on the data that you've entered. A little bit later in our presentation, we'll go through and just show you what this calculator looks like and how to make use of it. For those that have the links or have seen this before, it is on one of our main pages under power quality. I make use of this calculator daily. It makes my life a little bit easier than having to look through these tables like this. Okay. What I do tell some customers is just make a shortcut on your phone to this link, which you just add to your home screen. And if you're in front of a customer and you've got the meter data in front of you, you can quickly give them an estimate on what is the kVAR required for the site. Okay. This calculator will only give you the kVAR required. It does not know, do I need reactors or filters and so forth. And that it takes us to our next topic. Okay. So reactive power compensation, as we have mentioned, is done by injecting the opposite reactive power using capacitors. This is done by obviously injecting or inserting the capacitor at the required time. And our result is this kVAR reduction takes us there because the compensation came from the capacitor. But multiple power factors actually exist. So there are different power factors, what we'd call displacement power factor, which is this is the power factor between active power and reactive power strictly. And this is what we'd call the cost pi. In our worlds and evermore, as the invention of electronics continues, true power factor is between active power, reactive power, and distorted power. So I take you to a modified power triangle where we've got the S kVA, which would be your IRMS, your total current, your true current. You've got your displacement kVA, which is your fundamental. And we've got what we call, in this case, the harmonic current. Now, on the power factor correction system, without any sort of harmonic mitigation, in this scenario, we would only be able to correct the displacement kVA. But what about the rest? This between the S total and the kilowatt, this portion sitting here, that is what we would see as harmonic content. And how would we mitigate or correct that? So even if you try to correct the site to a 0.98, unless you're resolving this portion here, you will not get to that 0.98. So this takes us on to what we call introduction to harmonics. So as we know, power quality is evolving based on the load types. So what has happened in the last few years, the advent of nonlinear electronics, where AC is converted to DC voltage. This alters the way power is traditionally drawn from the normal sine wave. So during the AC to DC conversion, power electronics devices are switched for a fraction of each cycle, half cycle, causing voltage and current to be drawn in pulses to obtain the required DC output. So what does that mean? Our typical sites nowadays would have, as we mentioned, these non-linear electronic loads. So what are they? You can imagine a variable speed drive. So depending on the type of drive, would be depending on how many pulses it produces, and depending on the pulse type, it would affect what we call a harmonic order. So we have an example here between a 6, a 12, and 18 pulse, and the different harmonic orders that would affect. Switch mode power supplies, fluorescent lighting, arcing devices, all contribute some sort of harmonic into our network. So what do harmonics do? Harmonic currents may cause system losses that overburden the distribution system. This electrical overload may contribute to preventing any existing distribution from serving its full purpose or any future purposes. So some immediate effects, pending harmonic percentages, overheating of transformers or rotating equipment, conductor losses, a bad power factor because you could not reach the desired PF due to the harmonic content, depending on the harmonic overloading of neutral, unacceptable neutral ground voltages, distorted voltage and current waveforms, failed capacitor banks, breakers, fuses tripping. In a lot of cases, guys would have to double size the neutral to defy the negative effects of the third order triplet harmonics. So for us to understand or try and comprehend what these harmonics are, we'll go briefly or very light on the subject in this discussion. So we have a type of sequence in our AC network. So positive rotating, negative rotating, and zero. Each one of these is defined by frequency. So we know the fundamental, we know a 50 hertz. So depending on the type, they either rotate in the same direction as the grid, positive, or negative. They opposite to the grid, and then we've got what we call the zero crossing. So to describe those, so positive sequences, harmonics, the 4th, 7th, 5th, are undesirable because they are responsible for overheating conductors, power lines, and transformers due to the addition of the waveforms. They do not have the same phase rotation and the fundamental, and they'll circulate between phases. These are quite typical in our networks. To view it, you would need a recorder that can capture this data. Negative sequencing harmonics, on the other hand, they circulate between the phases, creating additional problems with motors, such as opposite phase rotation, weakening the magnetic field required by the motors, and especially induction motors. So these negative sequencing would be these. So we quite often would see 5th and 7th harmonics in our surveys. Another set of special harmonics, and these are becoming more and more, is what we'd call the triplet harmonics. They are multiple of 3, and they have what we call zero rotation sequence. These being 3, 6, 9, and so forth, they have what we call displaced by 0 degrees. These circulate between the phase and neutral. So unlike the positive and negative, which can cancel each other out, depending on the load profile, the third order or the triplen do not cancel out. Instead, it will add up arithmetically to the common neutral, which is then subject to the currents from all three phases. So when you would see a neutral, which you see current flow or overload seen, chances are you've got triplen harmonics on that side. The only real way to view that is through a power quality analyzer. So the result is that current on the neutral wire due to these harmonics could be 3 times the amplitude of the phase current. So we can see where this can become, dangerous or loss of those neutrals. As indicated, we would have a fundamental, positive, then we have a negative, and so forth as we go through the different harmonic frequencies. Typically on our recorders or any recorder, you want to record up to at least the 50th order of harmonics. So a brief overview of harmonic effects. So positive sequencing, forward, excessive heating. Reverse, motor torque problems. 0 sequencing, adds voltage or currents into neutral wire. All right. If we view this, all these waveforms we would see here, the fifth, as we mentioned, was negative sequencing. The seventh was positive. To some extent, these would cancel each other out if you sum them up. But the 0 sequencing that would exist would continue to exist and thus be present onto the neutral. So to visually display to you what this would look like, we've got our voltage waveform. So this is the ideal AC waveform there at 50 hertz, okay, over 20 milliseconds. The ideal load would have a current shape exactly to the voltage. So if we imagine we had a resistive load flowing at the same time, it would look something like this. And this would be the perfect world, and everything is at unity and there's no issues. These perfect grids seldom exist. Other loads are more common, which we've spoke about before: capacitive, inductive, and nonlinear, what we call our AC to DC conversion variable load. So in this example, if we imagine this was a waveform being measured on a variable speed drive, nonlinear loads are drawing currents from a grid that are not a perfect sine wave. So if we look at this waveform here, the current waveform, the diode rectifier in the load will be blocking the current flow in lower voltages, and only at a specific voltage would it let the current flow through. So in this diagram on this side, this is from a variable speed drive extract. We have an on time, and only at this on time is voltage output applied and at the right point, and current is allowed through. And that's what the waveform would look like. Now, as a few slides before, I had the different harmonic orders depending on the type of pulse from the rectifier. All these add up onto this waveform. So I have a brief example of what this might look like. So every waveform, doesn't matter how complex it looks, can be described with a series of sine waves. Each sine wave will have a different frequency. So this current waveform can be described as the current drawn at a specific frequency. So what does this look like? So we have our original 50 hertz. In this example, that's 75 amps. Now we have a 37 amps at 150 hertz being applied, which would then, if you see the difference here, increase the waveform because it's adding up. It's a third order harmonic. So increase. We have now, which is now decreasing the waveform. And as we carry through, each different harmonic order based on its current starts changing this waveform for us. It would be great to be able to show this real time on an oscilloscope, but we've only got this presentation. And as these harmonic orders all add with their different frequencies, they all have a current attached to it. And with all these attached, we have this resulting waveform. So the more harmonics, and we add them all up, the closer we get to the current waveform. This is for the first 50 hertz. Okay. So harmonics displayed with the frequency on the x-axis instead of time are called, in this case, a spectrum. So when you look at your power quality analyzer, it can output hopefully something similar to this at a specific point in time, at a specific load. So in this case, we have the fundamental, which was 75 amps. And then we have all the other currents adding up based on their frequency. All right. As we said, depending if they're positive or negative, they're either adding up or subtracting from themselves. And then we'll get what we call the total RMS, or what I mentioned on the previous power triangle, the total kVA, including the harmonics. So what is the total distortion in this example? The harmonic current divided by the fundamental, and we have a percentage, which is the THDI. In this case, 56% of that current or that waveform at that point in time is what we would consider as distorted. So all frequencies besides the fundamental are not useful for the load, so harmonics are useless. So that is what we would see as wastage. So we quite often reference total harmonic distortion, or THD, on meters, multimeters, power quality analyzers. They all have that same definition. You would have total harmonic distortion in current. It can be shown in different abbreviations, as we see here, or variables. But no matter what, that THD with the I always stands for the current distortion. And then we have THDU, which is the voltage distortion. Okay, and that would be displayed as a U or a V, depending on the product being used. Okay. So how does this all add up? Harmonics distortion from nonlinear loads, the THDI, is always created by the load. So current distortion will always be created by the load. What does this result in? Transformer losses, heatings, reduced transformer life, cable losses and heatings, tripping of breakers, as an example. Voltage harmonics in the transformer are created in almost all cases by your current harmonic. So it's based on the nature of a load. You will not know what this is without having the load running. All right. Now, obviously, if you've got a voltage distortion, all your product on that site will be affected by that voltage distortion. So that will reduce lifetime on equipment, additional equipment malfunction, and reduce productivity. So how do we fix this? We've got to look at current distortion, and we've got to reduce this by addressing the load that is causing the problem. All right. So there's different ways to do this. You can have what we call tuned filters, specifically sized against the system. That would provide power factor correction to a point. They are cheaper. To size these, as with any harmonic application, you would need recordings from the site. Harmonic mitigation transformers, this would be in new designs, no power factor correction benefits. And then what we're pushing more and more is what we call active filters. So these are ideal, but they are higher cost. Within our portfolio, it would be a tuned filter and an active filter. So again, how do we determine if a customer site needs some form of harmonic mitigation? It is advised, again, obtain a correct load profile of the facility using a dedicated power quality logger. 7 days, minimum 1 to 5 minutes, including all the harmonic orders. So as we saw on the previous slides, from the beginning to the end, across those 50, you want to see that profile, all right? And then similar to the normal power factor, again, peak kVA, peak kilowatt, the power factor ratio, the network voltage, and most importantly, THDI and THDU per harmonic order. With this data, and only with this sort of data, will you be able to say, all right, do I need a power factor system with reactors to protect the capacitor banks? Or is the content so high that I need another form of mitigation on the site? So maybe my site has got tripling harmonics. How do I protect my equipment from this? Then we'd look at what we call active power filters. Okay, what solutions have we got for this? As Electromechanica, we can do a normal power factor system with capacitors and reactors. There's also what we call a static VAR generator, and more there's what we call the active power filter. Okay, what is the main difference between all of these? Capacitor banks would be slower and they're not as dynamic versus an active power filter. A active power filter can do leading and lagging compensation and harmonic compensation. It does this by injecting the required currents in basically less than the half waveform, the 10 milliseconds, to smooth out that sine wave. In a lot of cases, it could be hybrids. The customer will need capacitor bank to correct the cost pi, and you may need an active power filter to correct the rest of that harmonic current. Okay. Where would this be installed to address this problem? In this example, we have a transformer coming in, main breaker, main bus line, and we have all these equipments that add to the harmonic profile. The CT would measure the requirement, give it to the active filter. The active filter would in real time be either capacitive or inductive, injecting the current to smooth out that waveform. Preferably in any of these configurations, and to be more cost effective, try to find the source that is your largest generation point and inject at that source for best practice. So what does this active power filter do? So it's a very high level view. It's got all its IGBTs in and rectifying circuits and so forth. The CT measures the uncorrected waveform. The unit itself, as I said, can be capacitive, inductive, and releasing energy to smooth out that waveform. All right. So if you were to measure at this point, that is what your waveform should look like versus that. So in this example, you can imagine if I had a whole lot of variable speed drives or whatever the case be, nonlinear loads, creating this harmonic profile, and I had other appliances connected here, I would optimally get as close as possible to this to give maximum benefit on any other appliance that may be wired onto that system. Okay. As mentioned, the current harmonic will result in a voltage harmonic, which will be seen by the total grid. A static VAR generator, it does not do harmonic compensation, but in real time, less than 10 milliseconds, it can be generating the reactive power required to be capacitive to do the correction. It does leading and lagging correction. So under no load, where the measured is equal, no reactive current. Capacitive is leading the voltage. It is continuously changing the amplitude, and the same with the inductive. Okay. A static VAR generator would be applied in aspects where you have very fast loads or changes that need to be addressed to get as close as possible to your perfect power factor. So for harmonics, as EM, we have the solution. So in our catalog, we've got this on page F14. These would come in a configuration of either what we call a draw type. What is draw type? Means I can rack this unit in and out. Fixed type would mean non-swappable. It's physically connected at the back, which would mean switching off to remove a unit. Each module is independent of each other. The only common point between all of these modules would be the current measurement. So each one would look at the current waveform, and it would do its work to correct that current waveform. These do come in different ranges and sizes. Typical sizes that we would be selling would be 50 amps. We do 75s. All right. The cabinets are stackable, as seen here, up to 7 units, depending on the configuration, can be stacked. Same with the fixed units. There is a range for 690 volts up to 100 amps. All right. The question might arise, is an active filter feasible to do power factor correction? Yes, it would be a very expensive power factor correction system. The 50, an example, a 50 amp unit, as per page F14, would result in approximately 36 kVAR, which isn't much. So purpose-built, use active power filters for harmonic mitigation, okay, 4-wire type systems. We do have a wall mount unit, same as the fixed, except these are, as we can see, you'd mount it on the wall, and yes, you can parallel a whole lot of units and have one common screen to check functionality, parameters, alarming, and so forth. The same concept is applied for static VAR generation. In this case, you would have kVAR rating. Note this does not do any harmonic mitigation. And the same would apply. You would choose your cabinet and add the relevant amount of kVAR into that cabinet. The SVG also comes in a wall mount configuration. So if you have an application that is fast switching, low kVAR, maybe you only need one or multiple depending on your site. These systems are connected in parallel. So we've got this cabinet fully loaded with 7 units. The maximum cabinet would be 525 amps on 7 modules. You can parallel up to 10 cabinets. Okay, so the more mitigation you would need, the more you could parallel up. So we've reached a point in the break. I think if there's any questions at this stage, while we have time before we take a 5-minute break.
Yeah, Arthur, we have a few questions here. Maybe we can answer some of them quickly. There's a lot of questions about the PV side. Then there's a question from Ms. Agun, why we connect the fixed reactor after the CT, but we connect the fixed capacitor before the CT.
Okay, if you could, I don't see this question. Where's it been posted? Or you can just read it again, sorry.
Okay, so the question is why we connect the fixed reactor after the CT, but we connect the fixed capacitor before the CT.
Okay, so on the PFC systems, you would measure the total load, and the reactor is there to protect the capacitor bank. So it would be wired in line at that injection point. I'm not sure if that answers that question.
It's a very general.
I think yeah.
So maybe we can respond to him afterwards.
Yeah.
Then there's a question in terms of the bearings of the motors. What are the measures to put in place to take care of the harmonics caused by the speed drives on bearings of electric motors? Are there instances where the speed drives are totally unwanted to the extent of using traditional motor starters like the DOL or Star Delta or auto transformer?
Okay, so on the variable speed drive, again, it's down to the type of a variable speed drive. So based on the discussion around the pulses, you would have a 6 pulse, 12 pulse, 18, 24. The more money you spend or throw at that variable speed drive, the smoother that waveform is going to be ultimately to the motor and to the grid supplying it. Different vendors of different variable speed drives have papers written about mitigation that will tell you need or prefer to use this type of filter or inductor in line with the supply to the variable speed drive, and then also other mitigation parts on the output of the variable speed drive. Again, it's how much money you throw in at the variable speed drive will depend on the quality of what it does on the power network. So to answer that, the manufacturer will have a scope on that variable speed drive to give you some direction of what size reactor to wire in line with the variable speed drive, what to put on the output of a variable speed drive. Do you need an additional EMC filter on that unit? All of these obviously add up to the cost. Okay.
Another one is, in your opinion, what is the acceptable harmonic level before the reactors or the filters needs to be installed?
All right, so the harmonic level is dependent on a few things. So if you took an example, a 1 MVA transformer, and someone told you, oh, you've got a 10% THDI, as an example. So the question would be, at that 10% THDI, what was the current or the percentage of the load of the transformer? Okay, because if you can imagine, if I had the 1 MVA and only 100 kVA at 10%, that is negligible. I would not even look at it. I wouldn't worry about it. But if I had 10% of the total 1 MVA, that's a different story. So as we said, the current harmonic contributes to the voltage harmonic. The proportion is the higher that THDI based on the total load of a transformer, the worse your voltage harmonic is going to become. The worse the total effect is for your site. But to shorten it and just give you the answer, we typically say THDI no greater than 10%. Okay. Voltage normally less than anything less than or more than 2-3%. Okay. If you don't have these reactors in place, remember the capacitor is going to see that voltage issue. It will see parts of the current harmonic issues, and basically what will happen is that capacitor is just going to work a lot harder. Depending on how hard it needs to work, it might be exceeding its standard or manufacturer limits. You could see that very easily if you bring in a capacitor and say it's 25 kV and you measure the line current, you look at what the manufacturer says it should be. If it's higher, then there's an immediate sign that something's going on here. And then you need to do the logging. Almost every single system or high percentage of systems now all require the reactors. And this is due to the nature of the loads. Everyone's gone to LED lighting, to variable speed drives, to multiple different non-linear AC to DC conversion systems on the load to save power. But in doing this, the power quality is being reduced. This poorer power quality is then seen by your let's call it the Alvi grid, and then also the capacitor system.
Okay, there's a couple of questions about PV, but I think we should wait till the end to answer these questions. Okay. Right, so maybe I propose that we take a 5-minute break, fill up the coffee, okay, and then we return in 5 minutes time.
Okay, I'll leave us with the little video here for during the break for those who aren't walking away from their screens.
Yeah, Arthur, I think 5 minutes has come and gone, so maybe it's time to start again.
Okay. All right. Thank you. Thank you for everyone. All right. So now we move more on to which solutions are required or best suited for power factor correction, which are all offered by EM. So we will have what we call standard switching, and we'll talk about the controllers and contactors. We'll do fast switching, configuration, overview of these systems, the capacitors, reactors, and what we would call the build systems we do. Okay. We've also generated an installation and commissioning guide to help our customers install these systems. So as EM, we will only use and we install what we call the Lovato range of DCRL controllers for what we'd call smaller systems. So quite often in what we call a wall mount system with smaller steps, slightly simpler sort of solution, we would use what we call the DCRL. And depending on the model, we have different steps or built-in steps on the unit. So what is quite important on these units, the DCRL versus DCRL 8, yes, the look is similar. Both have the functions of expansions on via I/O, be it digital, inputs, outputs, additional steps, communication, modules. If you're going to link your power factor to a SCADA or a system that's a BMS that needs to monitor this, these controllers use TRMS and will provide the electrical measures, including voltage and current THDI percentages up to the 15th order. A wide power supply range. These units are also suitable for MV installations. So quite important. The more useful component on the controllers is what can it display to me? What is the statuses of my controller? So with the screens provided by the DCRLs, you can obviously see your power factor, where it's at, your reactive power steps. We've got the status of our steps to tell me which bank has been stepped in. It will show me what if the unit is in manual mode or automatic mode. The cooling fan status, when you use the function within the controller, any active alarms that may be within the system. And these can be configured to some extent. On the fronts of these controllers would be your operations between manual and automatic, allowing you to scroll through the displays against the various variables to see measures such as min-max values on voltages, harmonics, and so forth. Quite an important part is you may have started with a system that only has 3 outputs or 5 outputs, and now you've got to add more steps onto it. This can be achieved by using what we call EXP modules from Lovato, and these modules vary. You can have a 2 or 3 relay output. So taking a DCRL3 with a 3 relay output, we can go up to 6 steps. The 5, 8 steps, 8, 14 steps. All right. So at the back of these controllers, you will see this little card that can slide in here, or module. And depending on the controller, there's X amount of slots available to you to do this. Okay. So the DCRL range, as mentioned, between the 3, 5, and 8. This controller only uses a single CT input for measurement and 2-phase reference for voltage. All these controllers will need a clockwise phase rotation connection. All right. quite important when using these sorts, because that's typically the problems we have on sites. Customers did not check this when they connected the system, and then the system is just not operating correctly, but it's due to what we call phase rotation. All right, so clockwise phase rotation at measurement point. All right, so CT measures the load, and it will tell, obviously based on voltage, and it will inject the relevant capacitor banks. Okay. Noted the inputs are up to 600 volts, auxiliary up to 440. Then our Rolls-Royce controller, which we would use on all our reactor-based systems and non-reactor-based systems, the floor mounts, the DCRG8 controller. By default, it would have 8 built-in steps. There's also a version which we call the DCRG8F, which has got 8 built-in static outputs. So this is what we would use for fast switching systems, which we will cover in later stages. Again, the optical front port for your programming and so forth. Also expandable, but up to 4 modules. So much greater than the DCRL5. Also larger voltage measurement, up to 720 volts AC. Quite unique, and I don't know if there are other competitors that have such a function, is the master-slave function, which I will discuss later. It can be used if required in a single-phase switching environment. It can be used for inductive type power factor systems. We personally have never installed one of those. No real requirement has come up. Real-time clock, obviously for logging events up to 250 events, which is quite useful when you're troubleshooting these things and the customer phones you and says there's some issue. The event log is the history log. It will tell you, all right, this occurred during this stage. All right. Expand this module or this controller with a module for what we call additional data storage. So if you got specific variables that you'd like to log, say volts, amps, kilowatt, and at a specific interval, you could put this expansion module into the mix. Quite important on the DCRG8 is obviously the screen is quite clear to tell you what is going on in the system. In this example, what is my set point, my total required kVAR, over or under, the conditions of my steps, the internal temperature measurement. My favorite is the current harmonic waveforms that you can see on the controller. Quite important when you're trying to troubleshoot some systems where customers may have not used reactors, and due to protection settings that we have placed inside the system decides, no, I'm disconnecting because I'm not happy. Quite often I would go into this graph page and I could see right there, without using any other power quality analyzer, that, wait, you do have a current harmonic. And based on thresholds set against THDI, I can disconnect the system. So it's quite flexible on taking different variables and customizing that as an alarm, and on the event of that alarm to tell the system to do this or do that, like disconnect the steps and so forth. Also, you can see step statistics, quite important, to see how many times that step has been brought in for maintenance purposes, maintaining your contactors and so forth. Again, interval service alarms could be set up. So if I reach a specific running hours or working time, I can put the system into a maintenance mode. and flag for maintenance. So the uniqueness of this controller is 4 voltage, all 3-phase and neutral measurement, 3 CT inputs, 5 or 1 amp selectable, where I push the recommendation to make use of the 3 CTs based on those harmonic pages, which I'll explain later. Very important function. When you've exceeded the maximum or feasible amount of steps within a panel, or you have problems with space in your LV room, imagine you have a long LV board and it's not feasible to get all the power factor into one part of it, or you can't because you're retrofitting the power factor system in. So you're left with putting part of the power factor system on one side of a board to the left and another part to the right. A very unique feature that works great is what we call a master-slave function of the controller. So you have one master in the system where the CTs and the voltage pickup take place. It then tells slaves via RS485 comms to bring in their steps. So they won't have any current measurement on them. Only one master would be able to decide to your slaves to bring in their banks. A maximum of 3 slaves, and you can set up quite a large system with this. When we hit the MVARs, basically we start looking at these sort of solutions, because it's not practical always to have all this control wiring between your panel. It's easier to have a system on one side, system on the other, comms bus between the two, and the master tells the slave what to do. Applications for DCRG8, as we said, single phase power factor correction systems, medium voltage, which I will highlight, dynamic power factor, fast switching. So a DCRG8 or DCRG8F can be used for fast switching systems, which we will discuss further. And if you need to do reactive power compensation with inductors, you could use a DCRG8 inductor. Expandability, again, 4 modules, max. This allows for additional relay steps, for standard contact switching, expansion for static switching, so for fast switching via thyristors, digital inputs, digital outputs, relay outputs, analogs. So very flexible. If you have a scenario of on a specific input, say disable the system or change the set point. So we've done that a few times on a specific condition. I don't want to be at 0.98, change my set point to 0.85. That can be done. The input receives the trigger based on a condition, and then the set point can be changed until that condition clears. On analogs is if you had external probes or multi-tier panels and you want to measure the temperatures within those separated panels. All right. Quite important, more and more customers want visibility of their systems on the network, on their SCADA, in the cloud. These controllers do have all the necessary expansions to be able to do that, be it RS485 Modbus or Ethernet, Profibus, and modem capability to extend that function. The controller can also take the data logging module, which will allow you to log specific variables at a specific interval for audit purposes. So on the DCRG8, based on your expansion types between the different modules, we have the maximum total steps you could build. So on a standard contactor-based switching system, up to 18 outputs. Remember, that's not our limit. If I want more, I can just link to another slave controller and expand on that. Okay. If I'm using what we call a hybrid between relay and fast switching, thyristor switching, depending on my combination of modules, this would be, say, 8 contactor switching and up to 16 fast switching channels. The DCRG8F was specific, more built for fast switching systems. So out the box, you are able to have 8 fast switching channels, static channels, and these are expandable up to 24 outputs, depending on the modules you've selected. Okay, it can also support relay outputs depending on your configuration. Okay, what makes this controller unique and special for us? We always push for full 3CT installations to get true, more accurate, better defined measurement and control of the system, and then 3 voltage pickups. So if I had 3 CTs installed, if I was to go to my harmonic page on the controller, I'm able to see each phase's condition. If I only had a single CT, I could be missing the conditions of the other phases on the harmonics page, as per example. The DCRG8 can be considered a power analyzer. It can also be a kilowatt hour meter. Obviously, it's not for your billing purposes, but it is there to give that data. In our example, we have here just up to 8 connection methods through relays to the capacitor banks. Okay, so total site is being measured, controller makes a decision, and it brings in the required reactive power to compensate for the total load. We have specific contactors that we would use for power factor correction. These contactors are equipped with what we call early make contacts, which are on this, let's call this auxiliary module that is here. It steps in during the closing phase, the resistors to limit the current flowing through the contactor. So these resistors are then excluded when the closing operation is done. So this will obviously increase the lifespan on the contactor and create a more reliable system. All right. When you're using reactors on the output side of this or input, you would then not use the current limiting resistors. So how does this look? We've got the limiting resistors wired in. The early MAC would close for a few seconds. I mean, not seconds, milliseconds. And then it would bring in the main contactor points for the circuit. So more and more, we get the requirement to make or build either just the rack or complete system of fast switching solutions. For this, we would make use of the Lovato thyristor, which we'll talk about now. So the problems of non-linear nodes are then more and more common. So what are these? You can imagine welders, presses, lifts, cranes. Most of these are AC to DC rectifiers or variable speed drives or on the network. These rapid variations conditions generate peaks of reactive power. Consequences, the same as standard power factor. There's additional stress on the transformer, transients, harmonics, and power losses. Examples of where dynamic power factor would be applied, as we said, welding machines, injection molding, fast presses. automotive functions, anywhere where that load is rapidly switching. So why would we use dynamic or fast switching solutions? In your conventional PFC, which uses contactors, the reaction time between the individual switching operations is typically 60 seconds due to the discharge time of the capacitor. So that it's not suitable for when you have fast varying loads. Also, the contactors would wear out a lot faster if you have a system that steps in very fast. Okay. So a standard contactor-based switching is what we call slow load changes. So large machine tools or drives and so forth. So the example would be if you had a spot welding application, as the weld is being made for a few seconds, the power factor system would say, all right, I need so much reactive power availability or capacitance, and it would bring in the steps. By the time a normal system brought in those steps, that load would already be gone, and then applied again. Now, in a contactor-based system, due to the discharge times required, say 60 seconds, there would be no availability in a power factor system to compensate. So eventually, a normal contactor-based system would add no value to correct your power factor. This is obviously dependent on how fast that load is switching. To see this, you would need to do your analysis on your load, and then define how much of that load is what we consider fast switching. So advantages of a reactor, we're talking milliseconds to switch in that capacitor bank. Due to zero crossing, it will switch without transients. So it prevents peaks of currents inrush from the capacitors of voltage thanks to the zero crossing features. Reduction of reactive power because you're getting closer to your set point faster. Improvement or elimination of the flicker and voltage drops. And then the other function would obviously be reduce or improving your power factor, reducing your kVA. Longer service life, thanks to contactless switching between the element and the capacitor, and an increased safety for a full system. So general characteristics, the item or the product can be provided from a 7.5 type to 120 kVA. We have different voltage ratings depending on your system. The device does have built-in current monitoring functions for diagnostics and protection of the banks. They are by default ready to use. I would always advise tweak your safety settings based on your requirements. This can be done via the NFC. So using the Lovato app, you can pre-program all your thyristors. So if they're all the same, you could copy paste that program across each thyristor. The front infrared port is where you would use the Lovato configurator or apps to connect to and actually view the inside of this thyristor for parameter settings. Additionally, you can give it a comms card RS485, which is then compatible with the previous discussed VCR-G8F. The zero crossing feature. So due to the electronic firing of the thyristor, the switch will bring itself in when the potential difference between the mains voltage and the residual voltage in the capacitors is equal to zero. This allows for minimization of current peaks on the caps, right? Obviously, that makes best sense for high number of switching operations where equipment is sensible to overcurrents and overvoltage transients are present. All right. So due to this transient free, that the wear and tear on the capacitors are reduced. With the new thyristor, it can be placed in any position due to internal fans or heat dissipation. So it's a lot more flexible than before. They are designed for continuation of current overload of up to 140% of the rating of the module. Features, again, internally inside the unit, there are a lot of settings for protection settings, THDI level that may be too high, a current limit, a voltage limit, operating hours, multiple sequences or measures that can be used to be programmed as protection thresholds on your capacitor bank. So, as I said, current, voltage, internal temperature, external temperature if you use a probe, THDI, and so forth. Also, based on measurement, due to internal current measurement, what is the life left within that capacitor that it is switching? When you expand the unit with the RS485 comms to the controller, what that allows is, historically, a lot of thyristors, and most, don't have this sort of feature. So you would not have any data coming from each bank. With the expansion of the 485, statistical data from the inside of that thyristor is now presented to your controller. And that can be presented further to the SCADA system or the measurement system. All right. Very valuable data for the customers that are really interested in what's happening at each bank level. The wiring options on the thyristor. So we've got our mains in reactor cap. We've got our auxiliary supply, programmable outputs or inputs, depending on a condition. Our control could be a DC control or dry contact, external or optional temperature module for additional condition monitoring and expansion. All right. We would typically use a dry contact, and for customers that want the advanced features back to the controller, the 485 option. So we've covered the controller and the thyristors available from Lovato, and the typical or the software that we would use to configure or remote control view those product lines is what we'd call Synergy Express. So connecting to the device, depending if it had a comms module inserted or via the infrared module, you would plug it into the device. Almost all the Lovato product lines, controller-wise, would have this diagnostic port or this interface port. Products that can expand by comms, all can make use of this software. So what is the purpose of the software? So as I troubleshoot the customer site, I can go check or modify parameters. I can save those parameters to file for history purpose. So I know what I did on that site. I can monitor in real time what's happening at that point when I'm busy troubleshooting, which is very useful. You can trigger commands. So say you're testing a genset controller, or in this case, a power factor controller, to be able to set steps on and off and view the response in the system. When connected live to trend, we can trend variables. So these can be trended in real time back to your PC, which is connected to the device. Again, export or saving the alarms list and events, which is quite handy when you're troubleshooting. And then if you're using the memory module to configure and collect data. The important takeaway from this Express software is is that it is used across the whole Lovato product range. So anything of comms, Express can be used for any one of these functions that we've just spoken about. To set it up, to save it, to view in real time what's going on with it. It's a very great tool for when you're working on these systems. Okay, so we've moved over from the controller and the contactor and power supply. And as Electromechanica, we're the agents for Electronicon. So what makes the cap special? It's neutral gas. There's no oils or anything like that in there. So makes it very safe. Electronicon uses what we call stacked windings in their configuration. So as with most capacitors, as this capacitor sees an over voltage or some sort of short circuit, the dielectric within the cap is what we call self-healing. So when there's an occurrence and there's voltage breaks down between the channel, this will release a type of short gas or burst or whatever we want to call it, and that spot will fuse closed basically. So that's what capacitor manufacturers would refer to as self-healing. Now, as with any capacitor, the self-healing event can only occur so many times. So depending on how many times transients or over voltage events, all this occurs onto the capacitor, there will be a pressure build inside this capacitor. When pressure builds up, depending on the capacitor, it will create a disconnect from the different phases. This is very important for a safety mechanism. So in the event of multiple, say, over voltages and a lot of self-healings occurred inside the unit, the pressure buildup will force the capacitor to stay open and remove itself from the circuit. Okay. As EM, we stock the units from 400 volts to, let's say, 800 volts. What I want to highlight on the different ranges is, and which is quite important, is the statistical life and over voltage conditions that are allowed. So if we look at the 440 volt rated continuous use, the statistical life is greater than 100,000 hours. If that site was to see an event of a higher voltage, you have permitted over voltages on these capacitors. All right. So this section is your operating section, and think of this as a bit of a safety net if something was to occur on those sites. I think the big question that resides here is depending on the customer's network, which capacitor to use. And most importantly, these permitted over voltages, your controller, your solution, your system shouldn't see or should prevent and protect the capacitors before this already happens. So using a DCRG8F, we've got, or just DCRG8, we will set up these safety functions. So we will say at a percentage of the network voltage, disconnect that system, all right? So as much as any capacitor has its ratings, your protection resides inside your controller. And more often than not, customers do not make full use of all the protection systems that are allowed within these controllers. So that takes us on to how do we protect our capacitors otherwise from harmonics. In this case, we would use detuned reactors. So this prevents harmonic amplification caused by resonance and avoid the risk of overloading capacitors. All right. These are wired in series with the capacitor banks. So we as EM, we have 7% reactors as an example. And on the system, we would wire those in series with a capacitor. Remember, that reactor is not a filter for your site. That reactor is there to protect your capacitor. All right. So it eliminates harmonic amplification. It will, enhance the life of a capacitor, and it will bring stability on the voltage back to the network when that unit is stepped in. So a quick view of what the reactors look like that we apply. We are able to source pretty much on any rated voltage and kVAR up to 100 kVAR. So when customers have some sort of specific, they can ask us, they can say, I want 14% with 55 volt network. We have access to all these solutions. So what we've got is, I'm just going to switch the slide here now. We have a sales brochure which we like to share, and it is available on our website for download. Within our brochure, we have the power factor calculator, which I've indicated. On this calculator, so you are able to either go to the link while we wait for it to load, and you're able to enter the data that you require. We will overview the basics of harmonics and highlight that we have products for this. This snapshot or this high-level view is the typical assembly that we as EM would do. We manufacture these units locally. Some customers only buy racks from us with or without reactors, or they buy the complete system. We're quite flexible in terms of if a customer needs some customization or a larger rack, we can assist on conditions. We use an isolator as an example. If a customer wants a circuit breaker at additional cost, those sort of modifications can be done. In this example, this is a non-reactor based system, so it's a little bit smaller than our bigger systems. In all our floor standing systems, we only make use of the DCRG8, pre-wired with 3 CT inputs. What we also do for our customers is we'll rewire in a contact for when you're running on a generator to step out the power factor system if required. An overview of our racks, what they would look like. So we've got standard systems for 440 volts. So we will use the 480 volt rated capacitor, and we will build you a system with the kVAR indicated at 400 volts. Yeah. So we can build a rack of the different mixes up to 100 kVAR in this format. We can build racks with 7% detuned reactors. So this is for systems where it's more 5th and 7th harmonics. We can do a 14% rack or 14%, for higher levels of 3rd order harmonics. We can build a 5 to 5 volt rack, and we can do limited customization if you have a specific set or rule that you want to do with specific reactors. Here is a list of floor standing non-reactors that we build. We indicate up to 950 in a double panel. We can obviously build bigger than this. That is when we start moving to a master slave configuration within our panels. That's our standard 400 volt, 5 to 5, and then our harmonic based systems, 7% and 14%. Again, this limitation can be broken quite easily. We can do a custom assembly where there's more than 2 panels, 3, 4, depending on what your requirements are. We do build a wall mount series. which will be limited to the 150 kV. These are for the smaller systems. It's non-reactor based. Reactors are quite heavy, so it's not feasible to try and get them into a wall mount system. And then we indicate our actual reactors. Tools, quite important. Just brief view, loggers. We do sell a logger that can assist you in your audits. And for maintenance purposes, thermal cameras, clamp meters, when you're troubleshooting your systems or doing maintenance on your systems. On our main landing page, a brief view of the calculator. So customer can enter their volts. If you've got amps, kVA, or kilowatt as an example, so I've got a site, 170 kVA, existing power factor being 0.7, and I want to take it to 0.98. If I've got the customer's charge rate here, I will insert it. This is in rands, and I will calculate. Here, the kVA is already calculated for me. We upsize the systems slightly to round up the numbers. You'll have your existing profile and your corrected profile. So you'll have your where you were on your kVA, where you will end, and the reduction of amps. So quite handy, and you can just email this to yourself as a quick snapshot. All right, like I said, create a shortcut to this on your phone, and you can make use of the calculation at any time as long as you've got the internet. Okay. What we have also done with our systems, any system going out, we have developed a commissioning and maintenance guide for our customers. Quite often, people installing or end users might not be familiar with what is required on maintenance. We've worked extensively to create this guide to help our customers. These guides are inserted in our panels to help you with from everything from a guiding to cable sizing to transport to maintenance to spares that you may require. Important additional systems, quite often it happens, customers buy power factor systems and they forget the CT. So I'm an advocate for split core CTs. Quite often you might have quite a large bus bar or ACB and you don't want to be disconnecting all the bus bar work. Split core CTs are the way to go. Class 1, class 0.5, that's all available from us. It does make your life a lot easier and faster and safer just snapping in the CT than having to disconnect all the bus bar work on site. All right, the calculator and brochure are all available on our website under power quality and about power factor. If you have any questions or queries, you can email info@em.co.za or myself, Arthur S@em.co.za. I'm sure there's questions that we have not covered here. Please email me and I'll respond the best I can. All right, I think that covers us on the presentation side.
Great, thank you, Arthur. I think it's a great job to have summarized such a huge topic into a short space of time. A lot of information, and but well done. So there are a couple of questions still open. The issue is regarding the APF, the active power filter. Why is the current sensor installed after the feeder of the APF, while on a capacitor bank, the current sensor is after the main circuit breaker?
Okay, so on the capacitor bank, you need to measure the total reactive power, and then you got to step in those capacitor banks to correct. If you had it the other way around, you would be measuring your own injection point. All right, so that is why it's like that on the PFC system. On the APF, you could have it on the other side. for all purposes, all installations that we've done or helped customers, we want to measure the total load and then inject the correction. You can have either or on APF. It's really down to what is happening on your site. What is more practical, depending what's going on inside that LV board or wherever it is you're connecting it. All right, so that's not a must, but from my experience, I've just preferred to do it that way.
Thank you to Ed Visser. He reminds us about the fact that we can install insulated bearings into the motor. That is based on a question that was asked earlier in terms of the effect of a speed drive on the bearings of the motor. There's obviously no need to revert back to DOLs or star delta starters if a speed drive is needed. But if you have any issues with the motor, then insulated bearings can be installed. Thank you for that comment. Arthur, maybe a few words about the PV, if photovoltaic is coupled directly into the system. Just a general comment about that.
All right, so PV is obviously a quite highly discussed topic. So if you were to look at your load profile, your PV system is there to generate or assist on the kilowatt. A PV system is not there for your reactive power. So you will always need a power factor system if you've got bad power factor, because the inverter itself inherently cannot store energy and release when required. All right. On the harmonic side of it, the filter inherently, or the PV inverter inherently is not the generation of the harmonic. What it sees is the existing grid. So on a grid tie system, if you connect a PV inverter, what's its reference point to grid? It's voltage. So any voltage harmonic present will be seen by the inverter. Thus, the output issue is going to be a current harmonic issue. All right. And if you have a perfect grid internally, so imagine if you put a PV system on a resistive only grid, you probably wouldn't see any issues. So it's quite important that when you do your PV systems to check for this, because you could be amplifying this problem. So there are PV suppliers that now do push their own line reactors or onto connection points of those inverters. I don't see a lot of people doing it. At some point, once you've amplified it enough, other things start happening, such as synchronization issues with generators and so forth. So inherently, to answer, the PV inverter itself is not the generator of the harmonic. It is amplifying what is already there caused by the load. So either address the load using a inline filter, a passive filter, a harmonic filter, and you will see the improvement then on the PV side.
Great, thank you. I think we have answered all the questions. If there's any other questions, please ask now. What I also would like to say is, if you would like to have a further discussion on this topic with Arthur or Electromechanica, you can contact us at em.co.za, at info@em.co.za. Also, we'd like to remind you about upcoming webinars. We have run already quite a couple of these webinars, and there's still a few on its way. The next one up is on enclosures on Thursday, the 16th of July. Then we have another Socomec webinar on transfer switching, which is on the 23rd of July. And then a big one on Lavato power metering solutions, which will be on the 30th of July. Please go to our website to register. So I think there's one more question that's come through now. Mr. Alguin would like to ask a question. Can you?
I see there's a question on top. I think it's the same person. Can you explain when an energy meter in MV and we connect fixed capacitor to secondary?
Yes, from Mr. Ogin. Maybe ask your question. We're waiting for Mr. Ogin to Graham raised a hand. Let me see if I can activate Mr. Graham. Allowed to talk. No, he does not want to talk. Okay, I propose that Mr. Ogin, we contact us after the seminar, and then we can address it on a one-on-one with you. And then, as we said, that this presentation will be made available after this, and it will be sent to you. All right, then we'd like to say thank you for your attendance. Thank you for joining us during the seminar. We have also a poll that we would like you to activate. It is a couple of questions to support us in making sure that information remains valid and applicable to your industry. And so we appreciate it. Thank you very much. And then until next time, we say that's the end of the seminar now. Thank you.